A trajectory cuts across the solar system.
On the observatory's images, it is only a faint point of light, shifting slightly against a background of stars that do not move. Night after night, the telescope records another position, another measurement, another small correction. At first, everything appears ordinary.
Astronomers discover new asteroids all the time. Most follow paths that can be reconstructed with enough observations. One more object rarely changes anything.
This one appears destined to become another entry in that growing archive. The observations continue. Each new position sharpens the calculation. The software reconstructs a possible orbit, then revises it as more measurements arrive. The uncertainty shrinks. The path becomes clearer. What should emerge is an unusually long ellipse. Instead, something refuses to settle. The reconstructed orbit continues to exceed the limit that separates objects held by the Sun from those that are not. More observations arrive. The calculation is repeated. The answer does not change. Its orbital eccentricity reaches approximately 1.2. That number is enough. An orbit greater than 1 is not simply stretched. It is open. The Sun can bend the object's path. It cannot keep it. If the measurements are correct, no encounter with the planets can explain where it came from. No hidden gravitational interaction inside the solar system can reconstruct the same trajectory. The mathematics leaves only one conclusion. The object approached from interstellar space. It passed through the planetary system once. It will never return. Independent observatories continue tracking it as it moves away from the Sun. Their measurements agree with the original solution. The orbit remains hyperbolic. The conclusion survives every additional observation. For the first time, the investigation no longer concerns an unusual asteroid. It concerns physical evidence that material from another planetary system has crossed our own. The caseboard receives its first entry. A single trajectory. A confirmed interstellar origin. The orbit has been solved. The object itself has not. The object never appears as more than a point of light. No telescope resolves mountains, craters, or color patterns. Every physical clue must be extracted from something far less dramatic. A tiny rise in brightness, a gradual fade, another rise, another fade. The investigation turns away from the orbit. A different question now takes its place. If this visitor came from another star, what is it? The methods are familiar. Astronomers have classified countless asteroids and comets using the same approach. Measure how the brightness changes as the object rotates. Search for the faint cloud of gas and dust that surrounds an active comet. Compare every observation with known bodies already cataloged inside the solar system. There is every reason to expect the mystery will become smaller as the data accumulate. Instead, it grows. The brightness swings far more dramatically than expected. As the object rotates, it alternates between reflecting a great deal of sunlight and almost none at all. The difference is so large that the simplest explanation is an extremely elongated or highly flattened body. Whatever its exact three-dimensional shape, it is unlike the vast majority of small objects previously observed. One piece of evidence changes the investigation. The object is physically unusual. The search continues. If sunlight is warming frozen material beneath the surface, escaping gas should carry dust with it. Even a weak comet normally reveals itself through a faint glowing coma surrounding the nucleus. Infrared observations search for that signature. Nothing appears. No visible cloud. No measurable dust production. For a moment, The investigation seems ready to settle. Perhaps the visitor is simply an unusually shaped asteroid from another planetary system. One more measurement refuses to cooperate. As astronomers continue tracking its departure, the reconstructed trajectory begins to drift very slightly from the path predicted by gravity alone. The deviation is small. It is also repeatable. Something is providing an additional push. That behavior resembles the effect produced when invisible gas escapes from a comet, creating a gentle thrust. Yet the observations still fail to reveal the visible dust or gas that normally accompanies such activity. The evidence begins to divide against itself. An extreme light curve, no visible coma, a measurable non-gravitational acceleration. Each observation survives independent analysis. None comfortably fits beside the others. Researchers repeat the measurements. Independent teams analyze the changing brightness. The infrared observations continue to show no detectable dust. Separate orbital studies confirm that the tiny additional acceleration is real. The contradiction does not disappear. Only the explanations change. The investigation reaches an unfamiliar conclusion. The uncertainty is no longer caused by missing evidence. It is caused by evidence that refuses to agree. The case board grows. The first entry now carries 4 verified observations. Confirmed interstellar origin. Extreme rotational brightness variation. No visible coma. Non-gravitational acceleration. Each line is supported by measurement. Together, they resist a single identity. The first case cannot be closed. It becomes stronger precisely because it remains unresolved. Only another interstellar visitor can reveal whether these contradictions belong to one extraordinary object, or whether humanity has mistaken a single witness for an entire population. Another faint object appears against the background stars. The discovery itself is no longer extraordinary. Modern sky surveys routinely identify new moving points of light. What matters is the orbit. The investigation begins the same way it began before. Position after position is measured. The path is reconstructed. The calculation is allowed to settle before anyone decides what has been found. The answer arrives quickly. This trajectory is also unbound. For only the second time, astronomers can say with confidence that an object has entered the solar system from another star. The evidence table receives a second row. At first, it seems the investigation is about to repeat itself. The first visitor refused classification despite months of observation. It is reasonable to expect another interstellar object to behave just as strangely. With only one previous case, there is no other expectation to hold. The telescopes remain fixed on the newcomer. Something appears that never appeared before. A faint halo begins to surround the nucleus. As the object approaches the sun, sunlight warms frozen material beneath its surface. Gas escapes into space, carrying tiny dust particles with it. The once sharp point of light grows diffuse. A tail begins to stretch away from the sun. This is not an ambiguous signal. It is the unmistakable appearance of an active comet. The investigation changes immediately. Spectroscopic observations divide the light into its component colors. Within that spectrum, researchers identify the signature of cyanogen gas, one of the volatile compounds commonly observed in long-period comets born within our own solar system. Independent observatories repeat the measurements. The glowing coma remains. The dust tail continues to develop. The spectrum consistently reveals familiar cometary chemistry. Nothing about the object's physical behavior demands a new category. Only its origin does. The expectation created by the first visitor quietly collapses. Interstellar origin does not require interstellar behavior. One visitor crossed the solar system carrying a collection of measurements that resisted every familiar label. The second crosses it behaving almost exactly as astronomers would expect from an ordinary comet, except that every orbital calculation points beyond the Sun's gravitational family. The evidence table changes again. The first row still contains an unresolved physical profile. The second now carries a very different record. Confirmed interstellar trajectory, visible coma, dust tail, cometary gas. The two entries sit beside one another. Neither explains the other. Instead, each makes the other more valuable. If only the first object had ever appeared, scientists might still wonder whether every interstellar visitor was destined to be equally mysterious. If only the second had appeared, it could have been dismissed as little more than a familiar comet born around another star. Together, they accomplished something neither could achieve alone. For the first time, the investigation possesses a control specimen. Comparison replaces isolation. Difference itself becomes evidence. The question is no longer why one object behaves strangely. It is what kind of unseen population could produce both an unresolved anomaly and an entirely ordinary comet, then send each of them across the same solar system. The investigation changes without another telescope discovery. This time, the evidence begins with a recorded impact. Years before either confirmed interstellar visitor entered the astronomical catalogs, a small meteor struck Earth's atmosphere. It burned up almost immediately. No observatory tracked it across the sky. No telescope measured its brightness. No spectrum revealed its composition. For years, it remained just another atmospheric event. Then a different source of evidence entered the investigation. A declassified assessment from the United States Space Command concluded that the recorded velocity was high enough to indicate a hyperbolic approach. If those measurements were correct, the object had arrived from beyond the solar system before colliding with Earth's atmosphere. At first glance, the case seems ready to become the third entry beside the two confirmed visitors. It cannot. Unlike the earlier discoveries, there are no discovery images to examine. No changing light curve. No visible coma. No spectroscopic measurements. The investigation possesses only the reported velocity and trajectory derived from military sensor data. That immediately changes the nature of the evidence. Astronomers are no longer asking only whether the object came from another star. They are asking how different kinds of evidence should be weighed against one another. The first two visitors earned their place through repeated astronomical observations that independent teams could examine for themselves. This new case depends upon measurements whose full uncertainties are not publicly available. The evidence is significant. It is also incomplete. Rather than closing the question, it widens it. The evidence table grows again. The first row remains a confirmed interstellar visitor whose physical nature is unresolved. The second remains a confirmed interstellar comet that behaves much like those found within our own solar system. The third does not occupy the same category. Instead, it appears in a separate section. Possible interstellar atmospheric impactor. Velocity supported by a United States Space Command assessment. Scientific status still debated because the underlying sensor uncertainties cannot be independently evaluated. The distinction matters. The investigation preserves the difference instead of erasing it. Yet something larger has already begun to change. Researchers no longer spend all of their effort asking what each individual object is. Instead, they begin asking how many similar objects should exist, whether or not they are detected, Computer simulations combine the confirmed discoveries with the limits of modern sky surveys. How much of the sky is observed each night? How faint an object can current telescopes detect? How many fast-moving visitors would pass unnoticed simply because they are too small, too dim, or arrive from the wrong direction? The calculations point toward the same conclusion from multiple independent approaches. The known visitors are unlikely to represent the entire population. They are the fraction that happen to pass through a very limited observational net. The investigation changes once more. The confirmed discoveries stop being treated as isolated curiosities. They become samples, not samples of one unusual object. Samples of a much larger population that is mostly invisible. The evidence table changes almost imperceptibly. It is no longer organized simply to record what has already been found. Empty rows appear beneath the existing entries. They are not placeholders for imagined discoveries. They are reminders that future detections are expected. The investigation is no longer waiting for another surprise. It is waiting for the next witness. The evidence table remains on the screen. Nothing about its appearance has become more dramatic. 3 entries occupy its surface, each carrying a different weight of evidence. Beneath them, empty rows wait in silence. They are not predictions about what the next object will be. They are predictions that more objects will come. That expectation does not arise from optimism. It arises from arithmetic. The 2 confirmed interstellar visitors changed more than their own case files. They changed estimates of how frequently planetary systems eject material into the galaxy. Every collision during planet formation, every close encounter with a giant planet, every gravitational disturbance capable of accelerating debris beyond a star's escape velocity contributes to a slow exchange taking place across the Milky Way. For billions of years, stars have not evolved in isolation. They have been shedding fragments. Most of those fragments drift through interstellar space without ever approaching another planetary system. But given enough time, enough stars, and enough ejected material, some inevitably cross the paths of other suns. The solar system is one of those paths. Population models reconstruct this unseen environment by working backward from the evidence already collected. If telescopes have identified only a handful of visitors, despite observing only part of the sky and only down to certain brightness limits, then the true number passing through the solar system at any moment must be substantially larger than the number humanity has actually recorded. The confirmed discoveries become calibration points. Not because they reveal everything, because they reveal enough. The next generation of observatories has been designed with exactly this problem in mind. Future surveys will repeatedly image nearly the entire visible sky with greater sensitivity than the systems that discovered the first confirmed visitors. Instead of waiting for rare accidents, astronomers expect to build a growing catalog of interstellar objects moving through the solar system. Each new detection will immediately join the evidence table. Some may resemble Borisov, displaying familiar cometary activity despite their distant origins. Others may resemble ʻOumuamua, presenting combinations of measurements that challenge existing categories. Some may reveal entirely new behaviors that neither of the first confirmed visitors displayed. The investigation no longer depends on any single object. It depends on accumulation. The meaning of the evidence table has changed for the final time. When the first entry appeared, it recorded an impossible trajectory. When the second appeared, it became a comparison between 2 independent visitors. When the third evidence class was added, it forced scientists to distinguish between different standards of proof while looking beyond individual cases. Now the table serves another purpose. It is no longer a record of extraordinary discoveries. It is a working archive of material that originated around stars humanity may never reach. Each confirmed interstellar object carries physical evidence shaped by another planetary system before beginning a journey lasting millions, or perhaps billions, of years through the galaxy. None tells the complete story of its birthplace. Together, they reveal something larger. The solar system is not a sealed neighborhood moving alone through space. It travels through a sparse but persistent stream of planetary debris exchanged between stars over cosmic time. Nothing about the Sun has changed. Nothing about its planets has changed. Only the investigation has. The first confirmed interstellar visitors did not solve the mystery of where these objects come from. They established that humanity has begun collecting physical evidence from planetary systems beyond its own. The evidence table remains. Its final rows are still empty. The table waits. No new entry appears. That is the final state of the investigation. The first confirmed visitor established that material from another star had physically crossed the solar system. The second demonstrated that interstellar objects could not be understood through a single example alone. The third evidence class broadened the investigation while preserving the distinction between confirmed astronomical observations and evidence that remains scientifically debated. From that point forward, the direction of the research changed. The question was no longer whether interstellar objects exist. The question became how many have passed unnoticed, and what each future detection will add to the growing forensic record. The investigation remains open because reality does. The next confirmed interstellar visitor will not begin a new story. It will be placed into an evidence archive that already exists, compared against the trajectories, measurements, and physical behavior of the visitors that came before it. The first entries transformed an isolated anomaly into the beginning of a measurable population. The empty rows remain because the archive is expected to grow. The narrator leaves. The evidence stays.